finish it off in the next few minutes and go on to something else. Please take note that on the 30th, that's not this Friday, but the Friday of next week, I won't be here, so the lecture has to be cancelled. But there will be a make-up lecture. It'll have to be one evening at 5:30 or 5 o'clock. Can't be helped. The other thing that I need to tell you, if I can get cleaner.
Me too. Would you go to that? I don't. I won't learn anything.
Maybe there is somebody here that does want to record and scan and maybe send it to
I'll probably go.
The other thing that I need to tell you is just to finish off what I was saying about NMR spectra at the end of the last lecture. What I was telling you was that if the chemical shift difference, which I represent by this delta nu, if that chemical shift difference in Hertz is a lot bigger than the coupling constant, then you get what are called first order spectra. And those first order spectra can be interpreted by this n+1 rule. But if the chemical shift difference between the signals is small, they're close together, and the size of that chemical shift difference is comparable to the size of the coupling constant, then the spectrum is much more complicated. And for some arrangements of atoms, you need very, very complicated calculations to work out what the spectrum is going to look like. Don't worry about that. You don't have to know any of this. I just want you to be aware that the spectra that you will deal with are what are called first order spectra. And I'll tell you something else. If you buy a small NMR machine in which the magnet's not incredibly powerful, and you also buy a very expensive NMR machine in which the magnet is much more powerful, and you take the same compound and run it in both machines, as the power of the magnet increases, a given spectrum approaches more and more closely to first order. So if one is dumb but rich, you buy a big machine because most of the spectrum you're going to run will just be first order. If one's poor and clever, you can get by with a small machine. The spectrum will depart somewhat from first order, but if one thinks about things enough, one can interpret what's going on. Of course, it's better to be clever and rich. Okay, so you need to know that the spectra that you're going to deal with have frequently been chosen so that they're not too complicated. The other thing you need to know is something about compounds that have OH groups and NH groups in them. If you look at the spectrum of ethanol, you would expect to see three signals, one for the methane, one for the CH2, one for the hydrogen on the oxygen. And indeed, you will see three signals. So let's get the TMS reference signal. At about 1, you'll see a triplet corresponding to 3 hydrogens. And at about 3.5, you will see a quartet corresponding to 2 hydrogens, and depending on the concentration and the temperature and a few other things, you will see a 1 hydrogen signal. So that's the pattern. Now when I tell you that, immediately you're going to ask me, why isn't the hydrogen of the OH split? Because if you count bonds, 1 bond, 2 bond, and then 3 bonds, that's 3 bonds away from a CH2. And you would expect that hydrogen to be split into the triplet, N+1. And in fact, if you have very pure ethanol, you will get a triplet. But ethanol as ordinarily run gives you a slightly broad singlet. What's the reason? The reason is that in ethanol molecules, let's write another one down here, and let's write yet another one down here. I don't mean to imply that they're all lined up neatly like that, like soldiers in a column, but there are loads of ethanol molecules. It turns out that the hydrogen on this one doesn't actually stay on this oxygen piece. It moves. Sometimes it moves onto this one, or it moves onto that one. And so this hydrogen, at one instant, might experience a particular orientation of the two little magnets represented by those hydrogens, but the next instant, it's on this molecule, and it's experiencing the two little magnetic orientations of these two, which can well be different from that, in the next instance on this one. So because it's moving around so quickly and changing its environment so quickly, it sees an average environment. And an average environment is a single environment. And therefore you don't see the splitting. However, if you have very pure ethanol, no trace of acid, no trace of base, the glass of the tube has been carefully freed of acid and of base, then you do see the triplet, because then the exchange is slow. And there's another thing you'll notice about OH signals of alcohols, and that is they move around. If you measure the spectrum now, comes at a certain position. If this afternoon you measure the spectrum and get a slightly different concentration, signal will be somewhere else. If you had exactly the same concentration, exactly the same temperature, and exactly the same solvent, the position won't move. But the position is sensitive to the concentration. Why? Because if the concentration is high, you have a lot of hydrogen bonding between the molecules. If the concentration is low, you have less hydrogen bonding. And it turns out that hydrogen bonding causes de-shielding. In other words, the more hydrogen bonding you've got, if the concentration is high, signal moves this way. The less hydrogen bonding you've got, moves the other way. Now the same sort of arguments apply to hydrogen on nitrogen. So these are things these are complications in NMR spectra that involve what are called dynamic processes, things that are moving. The hydrogen on the OH is moving unless you take special precautions. And if its environment is changing quickly enough, the hydrogen sees only an average environment, and if you've got a bunch of orientations, magnet can be this way, magnet can be this way, next magnet can be that, next magnet can be that, next magnet can be that, and so on. You've got millions of them. The average is just one orientation. And so you don't get splitting. So that's the story of that. And the hydrogen bonding business, as far as I can tell, it's not fully understood why hydrogen bonding produces de-shielding, but it's certainly an observed phenomenon. When you have hydrogen bonding, it moves to the left downfield. When you remove the hydrogen bonding, it moves upfield. So that's the story for NMR, and I think that's enough about NMR. I've given you a number of exercises, and probably by Monday I will give you a few more. I want to move on now to the next topic, which is chapter 13. Now, I'm sure that you've all been exposed in the first part of this course, the Chem 261, to some conjugated systems. You must all have heard of butadiene. If there's anybody who hasn't heard of butadiene, please raise their hands. I don't see any raised hands. So you've all heard of that. And it's probably the most famous conjugated system. It's got a system of double, single, double bonds. I need to say something in more detail over what you had last term. The most famous reaction of a conjugated system is the so-called Diels-Alder reaction, which for these two components doesn't work very well, but for this compound works very, very nicely and gives you, as you undoubtedly know from the last course, the Chem 261, it gives you that compound with this cis stereochemistry. Can all of you at the back see this writing? Is it big enough? Yes or no? It is big enough, good. Okay, you're actually next week, I think on Monday, going to do a Diels-Alder reaction in the lab. And what you're going to do is you're going to take a conjugated system, I assume it's going to be butadiene or something similar, and you're going to take a single double bond compound, probably a double bond compound having electron withdrawing substituents like that one, and you're going to heat them together. And you're going to get the so-called Diels-Alder adduct. Diels and Alder were German professors. Diels was the professor and Alder was his student, subsequently became a professor himself. And in the publication that first announced this reaction, which is an extremely useful reaction, for which they both got the Nobel Prize, they made a very strange comment. They made the comment that they reserve for themselves this area of research. Of course, nobody took any notice. So I'm going to talk about conjugated systems, and this is one of the most famous reactions of conjugated systems. All of you have been exposed to conjugated systems because if you eat a carrot, one of the components, the colouring component of the carrot, contains a large number of alternating double and single bonds. Now, what is the simplest conjugated system, at least according to your textbook, and how can we represent it? And according to your textbook, the simplest conjugated system is a p orbital adjacent to a pi bond. So I'm going to draw that system, and I'm going to draw it in several different ways for you, in order to show you that there are at least a couple of ways of understanding the properties of that system. And by the properties of that system, I mean, is it more stable or less stable than you might otherwise expect? And why does it react in the way that it does react? Why does some piece get attached to, say, one end as opposed to the other end, or maybe it gets attached to both ends? So I'm going to explain all that. Okay, your textbook says, with some justification, that the simplest conjugated system is simply a p orbital adjacent to a pi bond. And it gives a few examples. Now, one of the examples is that. Another example is that. Yet another example is that. And as I've just indicated, butadiene. Now, how can one represent these compounds? Well, for butadiene, if I can skeleton of butadiene. What I perhaps can do is to use red for the carbon skeleton of butadiene. So why don't I do that? So that's the carbon skeleton of butadiene, and on it I have superimposed the bonds to hydrogen, and you know that each of the carbons is sp2 hybridized, and therefore that leaves on each carbon a p orbital. And I've drawn the p orbitals here, and each p orbital has an electron in it. And in the pictures that we often draw, we draw these lobes rather big so that this one overlaps with that one, this one overlaps with that one, this one overlaps with that one. So that in a sense, the cloud of electron density represented by these p orbitals overlaps continuously on the top and on the bottom. So that the cloud of electron density is spread out. If you take one of these 3 carbon systems, let me draw in the p orbitals. So this thing is a very approximate orbital presentation of that 3 carbon system. You can see again that this p orbital can overlap with that one, and this can overlap with that one. So again, the cloud of electron density is regarded as being all along the top and all along the bottom. If you have, there's another one, I can write up yet another one. Let's use exactly the one they use in the book. Let's write that one. This orbital is empty because it's a carbocation. But you can see in a vague way that the electron density here, the electron density there, they can sort of spread out into this vacant orbital. So once again, you can get a cloud of electron density covering the whole 3 carbon system. So that is a very, very simple picture of conjugated systems of a p orbital being next to a pi bond. Some of these systems are much more stable than you might otherwise think. And we need to inquire into the reasons for that. So I will do that in a moment. What I want to do at present is to remind you how to make, or to remind you of a reaction, a very important reaction that involves this radical. And that reaction is allylic bromination. If you take a compound with allylic hydrogens, that is to say a hydrogen on carbon that's joined by a single bond to a double bond. So these are allylic hydrogens. There are 3 of them. And if you treat it with this material, which is called N-bromosuccinimide, and if you heat the mixture or you shine light on it, you will end up with that 3-carbon bromine containing compound, an allylic bromide. And the question is, how does that reaction work? Well, that reaction involves this radical, and therefore it involves species in which there is a charge, or electron density cloud, extending totally over the 3 carbons. Now, I have gone into the mechanism of this in the past, but since, for reasons best known to the author of the book, he makes a big song and dance about this reaction yet again in this chapter 13, I will go over the mechanism again. And then when I've done that, I will give you a more sophisticated picture of the orbital representation of these species that have a p orbital next to a pi bond. The p orbital can contain 1 electron, or no electrons, or 2 electrons. If you work out the electron count for this, there are 2 electrons in that p orbital, as I will show you in a moment. Now, the picture that I've given you so far is a very, very primitive picture. It just shows you if you've got a big cloud, I'm just representing 1 lobe on this carbon, and another fat cloud representing 1 lobe on the next carbon. The 2 fat clouds can overlap, and if you've got one on the 3rd carbon, it can overlap. So in the sense, you've got a cloud covering all the carbons. So that you might think, and you would be correct, that the electron density is not localized in one place. It's smeared over all the carbons. So let me just clean the whiteboard here and show you the mechanism of that allylic bromination, and then I will go into a more detailed treatment of representing these compounds by these orbitals. Because if some of you have been following very, very carefully, you will see that these pictures can't be quite right, because in some of them I have more than 2 electrons in an orbital. You're only allowed to have 2 electrons in each orbital. You see in the allylic radical, the way I drew it, there's 1 electron in here, there's 1 electron in the p orbital on this carbon, 1 electron in the p orbital on that carbon, and I said that all these orbitals, all these lobes interact. So the electron density is smeared out over the whole lot. Whereas it's true that they interact, it's true that it's smeared out over the whole lot, but the way I drew it would lead you to believe that in that smeared out orbital there were 3 electrons. There aren't, there are 2. And so I've got to tell you where the other electron is while it's still smeared out over the whole 3 carbons. So what happens here? Well, if you take NBS and either treat it with a catalytic amount of HBr, and usually you don't have to do that at all because it's actually very difficult to get 100% pure NBS. There's always a little bit of HBr there. And if you do that, a pair of electrons will attach themselves to one of the oxygens. You'll get bromide coming out, and bromide will now react in this way to give you that species plus a very small amount of bromine. And it is in fact a very small amount of bromine that does the allylic bromination, because this thing with light or heat gives you 2 bromine radicals. And once you've got a bromine radical, I'm going to explicitly draw all 3 hydrogens. I'm going to make heavy dots for the 2 electrons in one of those bonds between hydrogen and carbon. Plus HBr. And now this reacts with bromine to give that plus a bromine radical. And the bromine radical comes back and attacks another molecule of this propene. And so the whole thing keeps going. Once you've started it, it keeps going. And it is a radical chain reaction. And in an ideal world, once you've started it would just keep going, and then suddenly it would stop when all the propene and all the bromine had been used up. And you wouldn't have to keep initiating it. You remember from last year when you dealt with Chem 261, you did a lilac bromination, and there was an initiation step, there were propagation steps, and there were termination steps. And in fact, there are termination steps, because sometimes this bromine radical, instead of attacking the propene, just combines with another bromine radical, give that bromine. And this radical, instead of being attacked by bromine, like this, reacts with bromine radical. So you don't generate any radicals. So you have to keep initiating this. So you keep heating it, you keep shining light on it. Now, why is it that this hydrogen and not these other hydrogens are attacked? And the answer lies in the fact that this radical is especially stabilized, which just means it's at a lower energy than you would otherwise expect, and therefore it is easier to form. Now, what I better do before telling you why it's easier to form is I better write again a mechanism for the radical bromination, but I'm going to write it in a different way so that you can very easily see that there are initiation steps, there are what are called propagation steps, and there are what are called termination steps. So I will clean the board and show that. Yes. I'm sorry, you will have to speak more clearly because your voice doesn't carry very far. Yes? This one? It stays there.
Also, is there in the first one?
It was here in the first. Did I not have it in the first one? Oh, okay. Wait a minute. I'm so sorry. It shouldn't be there. What a dope. There we are. It shouldn't be there. Now it all makes sense, I hope.
No.
Okay, let me write up this free radical mechanism in a different way so that you can see the stages. The NBS, the N-bromosuccinimide, its job is just to provide a very low concentration of bromine. So we will assume we've started off with a low concentration of bromine. And if you heat it or shine light on it, you will get 2 bromine radicals. This is called initiation. In other words, starting things off. If we now have a hydrocarbon, and it doesn't matter what R is, but R will have, well, why don't I write cyclohexene? It's much easier than for you to see everything. So we start off with a neutral molecule, cyclohexene, and a radical, Br dot, and we end up with a neutral molecule, HBr, and a radical. So the number of radicals in this step has not changed. This is a propagation step. This cyclohexenyl radical reacts with bromine to give you the observed product plus a bromine radical. So this is again a propagation step. In a propagation step, you start off with a neutral molecule and a radical, you end up with a different neutral molecule and a different radical. So the number of radicals does not change. And you can see that this bromine radical could come back and attack another molecule of cyclohexene to generate the cyclohexenyl radical, which could then attack some molecular bromine to generate the observed product and form yet another bromine radical. This bromine radical would come along and hit the next molecule of cyclohexene, and it would go on and on until all the cyclohexene was used up. And so all you'd have to do in a case like that is you mix the things, you take a light bulb, you flip it on, you flip it off, and in a few minutes all over. But it doesn't happen like that. You have to leave the light on. Or if you're using heat, if you're thermally initiating it, you have to keep heating it. And the reason is that there are some termination steps. And one of them is that 2 bromine radicals come together and give you a bromine molecule. So here, the number of starting radicals decreases, goes from 2 to 0. You start with 2 radicals, you end up with no radicals. That's a termination step. Another termination step would be 2 of these you see, you start with 2 cyclohexenyl radicals, you end up with this neutral molecule. And the final termination step that's not right, what am I doing? The final termination step is a bromine radical combining with a cyclohexenyl radical. So you start with 2 radicals, you end up with a neutral molecule. So because of those termination steps, you have to keep initiating the whole process. So that's a quick revision for you on allylic bromination. I just want to add one other comment. I made this comment in the first 2 or 3 lectures because I went over this in the revision. And that is that you might wonder why the bromine doesn't add to the double bond, because you have a low concentration of bromine, and you know if you add bromine to a double bond, the bromine adds to each end of the double bond to give you a trans 1,2-dibromide, or a trans-vicinal dibromide. So why doesn't it happen here? It's very, very strange. Well, the detailed reason is beyond the course, except I can tell you that if you work out the equation for the rates of these reactions, it turns out that the rate for the ionic addition across the double bond is much, much more sensitive to the concentration of the bromine than the rate of the allylic bromination. And so if the concentration of the bromine is very low, which it has to be for this reaction, the rate of addition of bromine to the double bond is also very, very low. So the amount of simple bromine addition to the double bond is very, very small. So that's the story. So it actually all makes sense, but a detailed understanding of why you don't get bromine added to the double bond requires some sophisticated kinetics, to use the technical term. And all this business of the low concentration of bromine was established by a Belgian chemist with the rather unusual name of Goldfinger. And Dr. Goldfinger took some cyclohexene, I think it was, and a stream of nitrogen, into which he introduced very, very slowly a small amount of bromine, and he bubbled these gases into the cyclohexene and shone light on the cyclohexene. And what he got was allylic bromination. And so that proved that at a low concentration of bromine, you get allylic bromination. Now, why is it that this allylic hydrogen is so easily removed? Well, the reason is that what's formed is especially stable. And it's especially stable because this single electron that's left on that carbon can be spread over several carbons, over this one, and this one, in the way that I indicated earlier today, in a very primitive manner. And I told you that it was a very primitive explanation because if you followed through the logic of it, you would see that this whenever I stand here, I get that. It's almost as though I'm being warned that something bad's going to happen to me. I might fall down. By the way, I just noticed there's a little tape recorder on here. A few people have asked if you can tape record my lectures. You're perfectly welcome to tape record them. If you want to videotape them, you can as well. And we can perhaps at the end of the course arrange for the Princess Theatre or Lugano Theatre to Chem 263 movie festival. The other day when I was walking in after supper coming back to the lab, I walked past the Lugano Theatre and there was an incredibly long queue snaking all the way around the corner. So I thought it was some really important movie, such as the Battle of Britain or something like that. Then I walked past and looked up what the title was, A Festival of Dirty Movies.
It's like, ooh, what's that? Never mind.
Okay, if you think very carefully about the very primitive picture that I put up
I can't remember it.
earlier today for this compound, which, just to make sure everybody's with me, I will just write out the structure in this sort of babyish little kindergarten way. When I wrote up the very primitive picture of that, if you had followed through very carefully what I was saying, you should have concluded that there were 3 electrons in this orbital that was spread over all 3 carbons. And that's not true. When you combine p orbitals, the number of so-called molecular orbitals, in other words, orbitals spread over the whole molecule, must be the same as the number of p orbitals that you combine. So there is a p orbital here, there's a p orbital here, as you know from last term's course, and there's a p orbital here. This one, as I've drawn it, has one electron in it. So I'm combining really 3 p orbitals, and therefore, by this rule, which comes out of quantum mechanics, which we won't deal with, I must end up with 3 molecular orbitals. In other words, 3 orbitals that cover all the atoms of the molecule. And if I got 3 orbitals, there's another problem. What's their energy? Are they all different energy? Are they all the same energy? Well, it turns out for this, they're all of different energy. So there are 3 of them. But each orbital can carry only a maximum of 2 electrons. So if there are 3 orbitals, let me just represent the energies like this. And I've got 3 electrons to feed into these orbitals. What I'm going to do is I'm going to put 2 orbitals in the lowest energy level and 1 in the next energy level. And there's a quantum mechanical rule that says if you've got 2 electrons in the same orbital, they've got to be of opposite spins. Don't worry about that. What I want to do now is to draw a much more honest picture of the orbitals using these lobes so that you don't incorrectly assume that the molecular orbital I've drawn has 3 electrons, because it doesn't. So let me draw it like this. Now, I've drawn p orbital lobes, and I've put some pluses and minuses in.